In pure topology, we strip away familiar concepts like distance and rigid angles. Instead, we study proximity and shape using only open sets. Without a metric distance function to rely on, the standard tools of calculus and geometry fail. You cannot calculate a derivative or measure an arc length when distance is entirely undefined. This creates a central tension for mathematicians. We need a way to determine exactly when a purely abstract topological space possesses enough structure to be mapped with standard Cartesian coordinates. The methodology to resolve this is laid out systematically in Chapter 4 of James R. Munkres Topology, specifically working through sections 34 to 36. Bridging the gap between strict abstract set theory and concrete geometry is necessary to build the mathematical models used in advanced physics and real-world spatial mapping. To understand this progression, we look first at the end goal of these theorems, the concept of an m-dimensional manifold. A manifold is a Hausdorff space with a countable basis that behaves exactly like flat Euclidean space, but only strictly at a local level. Zoom out to a macro perspective, and that local flatness disappears. The global structure of the space might twist, loop, or fold in ways that standard geometric measurement cannot easily capture. Section 3.6 introduces a specific mechanical problem, proving mathematically that an abstract global structure of this kind can exist as a solid, unbroken shape in a higher dimension. If we translate an abstract manifold into a recognizable Euclidean shape, we solve the problem of visualizing higher dimensional mathematical phenomena. We give the abstraction a physical body. Translating a purely abstract manifold into a concrete space requires a rigorous mathematical mapping. Munkres defines a topological embedding on page 105. The function mapping space x to y must be injective, a strict one-to-one correspondence, and continuous. The critical caveat, restricting the destination to image set Z, the map must be a perfect homeomorphism. A homeomorphism guarantees that no topological properties are lost in translation. Tearing the space, fusing points together, or breaking continuous loops is strictly forbidden. Executing an embedding proves the abstract space is mathematically identical to a tangible, physical subset of the destination space. This leads us to the primary result of section 36, the embedding theorem for manifolds. The theorem proves that every compact M-manifold can be successfully embedded into an n-dimensional Euclidean space. Abstract manifolds are not theoretical ghosts. They can be perfectly realized as geometric structures inside a defined, high-dimensional reality. The difficulty in executing this proof lies in the continuous functions. We must manipulate these functions across the entirety of the manifold simultaneously. In pure topology, guaranteeing that a function behaves nicely in one isolated area is straightforward. Proving it remains unbroken when extended globally across the entire space is notoriously difficult. To achieve this global geometric realization, we need a mathematical mechanism that guarantees our ability to extend these localized functions safely. That mechanism is found one section prior, in section 35, the Tietze Extension theorem. Imagine we have a continuous function, strictly defined on a small closed subset. The theorem states if the overarching space is normal, we can extend that localized function outward to cover the entire space, without ever breaking continuity. A normal space is defined by a specific separation axiom. Any two disjoint closed sets within it can be entirely enclosed by non-overlapping open sets. If the space lacks this normal structure, or if the starting subset is enclosed, attempting to extend the function will force a tear or create an asymptote, similar to stretching the function 1 over x across 0. The Tietze Extension theorem acts as the vital mechanical lever. It allows mathematicians to safely stitch together local coordinates to build the global functions required by the embedding theorem. This logic rests on an even deeper foundation. Before extending functions or embedding theorems, we have to guarantee that the space possesses that required normal structure, and ask if it supports a measurable distance at all. To answer that, we revisit a foundational concept. Looking here at the text on page 122, Munkres formally defines a metric space using concrete distance functions, like the Euclidean metric, represented by the letter d. This brings us to section 34, and the Urysohn Metrization theorem, establishing the conditions where an abstract topology graduates into a metric space. Urysohn requires two conditions. The space must be regular and have a countable basis. Regularity dictates points and disjoint closed sets are separable by open sets. A countable basis limits the structural size, ensuring it isn't too large to be mapped. If these purely abstract conditions are met, the existence of a mathematical distance function is absolutely guaranteed. This establishes Urysohn as the bedrock of the entire chapter. It proves that rigorous set theory inevitably yields the metric infrastructure necessary to support normal spaces, continuous extensions, and physical geometry. By walking backward through the chapters of Munkres Topology, we uncover a highly interconnected and rigorous mathematical architecture. The Urysohn Metrization theorem guarantees metric properties from pure logic. That structure allows the Tietze Extension theorem to safely project continuous functions across the space. Those global functions provide the power for the embedding theorem to lock abstract manifolds perfectly into Euclidean space. Chapter 4 of Munkres demonstrates exactly how abstract axioms function as the blueprints for the physical geometry of our universe. If you want to support this kind of deep dive into mathematics, subscribe and like the video. Let us know in the comments which specific theorem from Munkres you'd like to see visualized next.